Hello and welcome to this next lecture in pattern recognition course. This lecture will complete our discussion on multi-layer feed-forward neural networks. So, just to recall the context, we have been discussing these so-called multi-layer feed-forward neural networks. These are networks where each unit takes a weighted sum of its inputs as its net input and passes it through an activation function, a sigmoid or a tan hyperbolic activation function, and that is how output is calculated. We have multiple layers in network, and layer by layer we will calculate the output. That is how inputs get transformed into outputs. So, as we saw, these multi-layer networks are good as model for approximating any continuous function. Right? Last time we actually saw a theorem which told you that if I want to approximate any continuous function, it could be as non-linear as we want, but any continuous function on a compact set in RM, the continuous real valued function, a compact set in RM, can be approximated by networks of this kind. Okay. So, the idea is that given training examples, we can learn the weights using the backpropagation algorithm. So, because we know that the structure is good enough for representing approximating most functions, we choose some structure of the network. Of course, you still have to decide how to choose, but we choose, let us say, one hidden layer and sufficient nodes, hidden nodes. Then we can, given the training examples, we will use the training examples to learn the weights and further to achieve the backpropagation algorithm. The backpropagation algorithm is nothing but it is an iterative gradient descent. The function we are optimizing, actually minimizing, is this sum of squared error, that is the empirical risk under the squared error loss function, which is simply sum of squares of the errors. By that I mean, for each input pattern, I calculate the network output, the desired output, take the difference, square it, that is the square of the error. We sum it over all the training patterns. This will be some function of the weights in the network, and we are minimizing this. We are doing gradient descent of this function to find the optimal weights. So, we are trying to find weights to minimize the squared error. Okay. The interesting thing is that the backpropagation algorithm, as we saw last time, it enables for a very efficient calculation of the gradients. To actually do the gradient descent on this function, we need to calculate all the gradients, that the gradient of the function with respect to all the weights, and the backpropagation algorithm, by a computation that is similar to a forward computation of calculating the outputs of the network given the inputs, by computation which has about as much computational complexity, what we call the backpropagation, it allows you to calculate all the partial derivatives of the error with respect to all the weights. So, that is how backpropagation allows us a efficient way to implement the gradient descent. Okay. Now, we also seen that in our under notation, the first layer is the input layer, last layer is the output layer. So, if you have only two layers, then there are no hidden nodes. So, it is like a perceptron or an Adeline. So, these are the linear models that we considered earlier. So, a two layer network can learn only a linear model. Whereas, the moment I put a three layer network, as we saw in the theorem in the last class, I can approximate any continuous function. Essentially, by putting one more layer, I am allowing myself to I am allowing myself a family of functions which can approximate any continuous function. Now, as we said, this is the motivation for considering multi-layer feed-forward networks. Of course, even though theoretically one hidden layer is enough, in practice we may need more than one hidden layer. But in any case, while a two layer network, in our notation, what will be a two layer network is can learn only linear models. The moment I have a hidden layer, I can approximate any continuous function if there are sufficiently many hidden nodes. So, in that sense, this forms a very nice parameterized class of nonlinear functions. Now, essentially, as we saw, by putting a hidden layer, the input is first getting transformed into the hidden layer, into the output of the hidden layer, and then these outputs are what go to the output node. So, if we look at the output layer and the layer just before the output layer, those two together will be a two layer network. So, that is essentially a linear model, but that linear model, the inputs to that linear model are not the original inputs, but the outputs of that layer just before the output layer. So, what the network is doing is essentially learning a proper internal representation, that is, while X is the actual given input, I transform into some other representation at the outputs of the layer just before the output layer. In that representation, a linear model is good enough. So, that is essentially what we are doing. Okay. So, let us take a little more, let us take one example to understand what we mean by proper internal representation. Okay. So, we will look at one function to understand this. Let us say we take the XR function. When we did the linear models for classification regression, we said say XR is one example of a classification problem which is not linearly separable, and hence a linear model is not good enough. What is the XR function? It has two inputs and one output. So, given two binary inputs x1, x2, we want the output to be 1 if and only if exactly one of them is 1. If both of them are 0 or both of them are 1, I want the output to be 0, but if only exactly one of them is 1, then I want the output to be 1. Okay. As we already know, a linear classifier or a two-layer network cannot really represent this, right. This is not linearly separable. So, a linear model cannot exactly represent this function, right. Let us try and understand in some sense, I mean it is a kind of proof, not really proof, a plausibility argument as to why a two-layer network cannot represent this. Let us take this a two-layer network, there is x1, x2, these are the input nodes. So, the output of this node is simply x1, the output of the node is simply x2, there are two weights and then the output node can have a bias. So, the final output I can get is f of w1 x1 plus w2 x2 plus w0. Okay. Now, when the two inputs are 0, the outputs are 0, right. At that time, let us say y should be low. Low means because I am using sigmoidal function, if the net input is small, then output would be small. So, let us say we put our weights w1, w2, w0 such that when these are 0, of course, w1, w0 does not matter because that will be 0. So, it will only be w0. So, w0 is sufficiently negative. So, that when both the inputs are 0, my y will be close to 0. Okay. Now, suppose x1 becomes 1. If x1 becomes 1, I want the output to go to 1. Now, what I change the net input, because x2 is still 0, this is still 0, the old w0 is still there. So, the only extra one is because this output is 1 now, I am getting an extra w1 in the net input. So, f of w0 should be close to 0. So, w0 should be some negative number, but f of w1 plus w0 should be close to 1. So, w1 should be sufficiently positive to overcome this minus w0, right. In the same way, suppose x1 is 0, but x2 is 1, once again y should go up. So, w2 should be sufficiently positive, so that if the net input is simply w2 plus w0, f of w2 plus w0 should also be sufficiently high. So, w2 should also be high and positive and high enough to overcome the negative thing of w0. I need w0 to be negative because when both of them are 0, I need y to be 0. So, given this, if both x1 and x2 are 1, now I get both w1 and w2, w1 plus w0 itself is enough to drive my sigmoid towards 1. If I add some more positive quantity, it comes closer to 1. There is no way it can, when both x1 and x2 are 1, the output can become suddenly 0. Because from when both of them are 0, the output is 0. Any one of them is 1, the output has to go to 1. So, both w1 and w2 weights have to be sufficiently positive. This implies that when both of them are 1, I have no choice but driving the output to 1. This is the reason why such a network cannot represent XOR. Okay. One way of looking at this is the following. We can think of XOR, the function XOR, having two parts. One is to detect when at least one of the two inputs is 1. The other part is to detect when both are 1. Let us say I only want to detect when at least one of them, when the two inputs is 1. That is a OR function. Out of the 4 possible inputs, only in one case it should be 0, other 3 should be in 1, and hence that is linearly separable. It is very easy to visualize, a square where one corner is in one class, the other 3 corners are the class. So, it is linearly separable. Similarly, detecting both are 1 is an AND function. Once again, if I take the 4 corners of a square, one corner is in one class and 3 corners are in the other class. This is also linearly separable. So, detecting when at least one of the two inputs is 1 is easy. Easy in the sense a linear model will do. Detecting when both inputs are 1, that is also easy. Once again a linear model will do. Individually each one is easy. Where is the problem? The combination that is difficult for the network without hidden layer. Basically, I have to detect the combination that at least one of the inputs is 1, but not both are 1. Right? That combination is what is not feasible to be done with linear model. This combination can be done with a hidden layer because this is the internal representation. Essentially, instead of representing x1, x2 as the two binary inputs, if I can transform that inputs into one that flags whether or not at least one of them is 1, other that flags whether or not both are 1. Now, this I can do in from inputs to hidden layer because that is like a small 2-layer network itself and it can learn any linear function. So, I can have hidden layers that can represent either this part or this part. With that internal representation, it is very easy now for me to represent XOR, because when this is 1 and this is 0, I want to flag 1, otherwise no. Whenever this is 1, I want to flag 0. Okay. Now, let us look at this. Here is one possible way. These are the input nodes. So, they give you 1 and 0s here. So, look at this hidden node, because both these weights are plus 1, it will get x1 plus x2. If both of them are 0, let us say if in this network, because we are using sigmoids for both the hidden nodes and the output node. So, let us say if the net input is minus 0.5, we will assume that sigmoid is close to 0, and if net input is 0.5 or more, then the output is close to 1. That is all we want to get. So, both x1 and x2 are 0, then is only minus 0.5 the net input. So, the output of this is close to 0. If at least one of them is 1, then it will be 1, net input will be 1 minus 0.5. So, net input will be 0.5. So, output will be sigmoid at 0.5, that will be close to 1. If both of them are 1, it will be even closer to 1. So, this hidden node is discovering whether at least one of the two inputs is 1. On this side, because I increase the bias, if both of them are 0, it will be sigma net input is minus 1.5. So, input is very close to 0. If only one of them is 1, then net input is still minus 0.5. So, it is still close to 0. Only both of them are 1, then net input will be plus 0.5. So, it will be close to 1. So, this node's output will be 1 only when both are 1. So, this is essentially indicating whether both are 1. This is indicating whether at least one of them is 1. If the output of both these nodes are 0, that means both are not 1 and not even one of them is 1. So, it is all zeros. So, when everything is 0, I want y to be 0, that is easy to achieve by having a negative bias minus 0.5. When output of this hidden node is 1, whereas output of this hidden node is 0, that means one of them is 1, but not both. Then I want y to go 1. So, I can put a positive weight on this. So, if I put plus 1 here, plus 1 minus 0.5, I will get a net input of 0.5 or more. So, the output will be high. On the other hand, when this becomes 1, this will also become 1 obviously. When this becomes 1, I am giving minus 2 into net input here. That will more than form this plus 1. Right? And hence, the output will now go to 0. So, this is how the hidden layer can now represent XOR. It has learned, it has right internal representation. Of course, here we are not showing any learning. I mean, whether there will be many other ways of representing this, but this is one kind of internal representation that I can learn in this problem. And the point of the example is that by having the right internal representation here, this is just a linear network. Right? This is just a linear model, and that linear model is enough because I have the right internal representation for the. Now, each of the internal representations themselves, because one layer can be learned with a bilinear model again. That is what I am doing. So, in all these networks, essentially they function because I can learn the right internal representations. Of course, if you actually take the squared error and do gradient descent, whether you converge to these particular weights is a different issue. That depends on how the gradient behaves, how the gradient descent behaves. Of course, there are other issues also. For example, suppose I have 1, 2, 3, 4, 5, 6, 7, 8, 9 weights. So, it's some 9-dimensional weight space in which I will be doing the optimization. Now, if I just switch these two nodes, I call this node as the second node in this layer and this node the first layer. So, if I interchange this node and this node, what it means is what was W1 and W2 earlier will now become W3 and W4. Right. So, just by doing some permutation of the nodes, I will be representing the same function, but in the weight space it will be different vector. So, obviously, there will be many weight combinations which will be good. Right. So, actually this kind of an optimization is hard optimization because there are multiple good minima. Okay. But we will come to whether the algorithm lands well or not, but all we are showing here is that this is what is meant by internal representation and this is what we seek to learn. Okay. We may learn, may not learn depending on whether the gradient descent gives us good local minima or bad local minima, but the idea is that this is how 3-layer network, multi-layer networks represent functions because they can represent the right internal representations. Okay. So, the hidden nodes here provide a proper representation of the input and hence the network as a whole can represent the XOR function. Okay. Let us move on. So, we can use multi-layer feed-forward networks both in classification and regression problems, and in either case we have to learn the network using the training set, right. That is what we have been doing all through the course. So, given some training examples either for a classification problem or a regression problem, I have to learn the model. So, here we have to learn the network, and learning the network is essentially learning the weights. The network structure has to be fixed beforehand. Then I learn the weights to minimize the squared error, and we can learn the weights using the backpropagation. Okay. So, let us quickly just see how I will use it for regression, how I will use it for classification, because we said that the network can arbitrarily approximate any continuous function. Of course, a classification function is not really a continuous function. So, we have to ask how do I use it for classification, and so let us start with how I use it for regression, then we can see how to use it for classification also. So, for the regression problem, what am I given? I am given data some xi di, xi belong to Rm, di belong to Rm prime. We need to train a feed-forward network to represent the function. This is what a regression problem is, right. In general, of course, M prime can be 1 or more. If it is 1, that is the standard regression constraint, otherwise we are learning a vector valued function. What do? We choose an input layer with m nodes because inputs come from Rm. We choose an output layer with m prime nodes because desired outputs are m prime dimensional, and we have to put some hidden layers and hidden nodes. We know theoretically one hidden layer is good enough, but practically we may need more than one, maybe very often we may need 2, and in each layer we need to decide how many hidden nodes we want. These are arbitrary decisions, and anyway they are the parameters of the algorithm. Once we have fixed a structure, we can learn the weights by doing gradient descent on the squared error loss using backpropagation. This is how we will learn the essentially to do the gradient descent we need to calculate the error on each training sample, and in this particular case there is absolutely no difficulty in deciding what the error is because the desired inputs are given, desired outputs are given. If I give xi as input, my training sample tells me exactly what should be the output, right. So, the error is always calculated using the desired function values, namely di. So, this is how we can certainly learn functions. Now, let us consider classification. In the classification case, I am just given feature vectors and class labels. Suppose I have a 2 class problem, my class labels can be +1, -1, can be 1, 0, whatever. Now, what should I use? For 2 class problem, there does not seem to be much this thing. We can think of our desired outputs set to be 0 and 1. So, I want to train my network so that when I put a class 1 pattern, the output is close to 0. When I put a class 2 pattern, the output is close to 1. So, that is why in the training sample, whenever you give me a class 1 pattern, I set the desired output as 0. Whenever I give a class 2 pattern, I set the desired output as 1. Now, we can train the network. Of course, the network cannot actually represent the discontinuous function, we classify it as a discontinuous function, but it will represent some continuous approximation to it. But after training, we expect it learns a function which whenever you put a class 1 pattern, the output will be close to 0. It may not be 0, but it will be closer to 0 than 1. And similarly, whenever you put a class 2 pattern, the output will be closer to 1 rather than 0. So, after training, when you give me a new x, I can threshold the output at 0.5 to decide on the class. If the output is closer to 1, I will say class 1. If output is closer to 0, I will say class 2. Okay. Of course, this 0 on 1 is arbitrary. I can as well use plus 1 minus 1, for example. If I use plus 1 minus 1, my output should go to both signs. So, I will use hyperbolic tangent rather than sigmoid at the activation function. So, with the hyperbolic tangent at the activation function, I can use the desired outputs as plus 1 and minus 1, right. So, essentially to use the network as a classifier in a 2 class case, my input layer will have as many nodes as the feature vector dimension. I am using only one output node. So, my desired output is a scalar, and I am saying either use 0 and 1 as the desired output or minus 1 and plus 1 as the desired output. If I use 0 and 1, I use sigmoidal activation. If I use minus 1 plus 1, I use hyperbolic tangent as activation. And if I use this, obviously after training, we threshold it at 0 instead of at 0.5 in this case. Okay. So, it is fairly clear how to use it for a 2 class classification problem. Suppose you have a k class classification problem, then what do I do? What should be the desired outputs now? There can be many possibilities. For example, we can still use a network whose input layer at the same dimension as the feature vector, output layer is still uses only one node, and I can give my desired inputs as 1 by k, 2 by k, k by k. So, if I am basically the idea is that whenever I put class I pattern, I want the output should be close to I by k, right. So, for example, if I have a 3 class problem, for all class 1 patterns, I will give the desired input as output as 1 by 3. For all class 2 patterns, I will give it as 2 by 3. For all class 3 patterns, I will give 3 by 3. The idea is now the network is learn a function, such that when I put a new vector x, if it is of class 1, the output should be close to 1 by 3. If it is of class 2, should be close to 2 by 3 and so on. So, I take the actual output, I ask is it closer to 1 by 3, or is it closer to 2 by 3, or is it closer to 1, and based on that, I can make my decision, right. So, after training, you can appropriately threshold the output to make a classification decision, but somehow this does not look very nice, right. This 1 by 3, 2 by 3 is very arbitrary, and if you have too many levels, it's not nice to expect the network to be able to do such fine distinction, right. As it is, what you are teaching is a discontinuous function, network can represent only a continuous function approximation, and then you have these fine levels and this 1 by 3, 2 by 3 kind of business looks very arbitrary. What else can I do? Here is another approach. Now, my input layer will have as many nodes as the feature vector dimension, and the output layer will have as many nodes as there are classes. If I am considering a k class problem, I will have k output nodes. If I have k output nodes, that means my desired output, when I give my training examples, my desired output should be k dimensional vectors, right. So, how do I give my desired output? If a particular example pattern, say xs, is in class j, then the corresponding desired output ds, which will be a k vector, will be a unit vector with jth component unity and all others 0. So, if xs is in class j, ds will be 0 0 0, 1 in the jth position and 0 0 0 0, right. ds will be unit vector with jth component unity and all others 0. So, this is how I specify the desired output for the jth. Now, this is interesting. Now, essentially, if you consider any one output node and say take the rest of the network connecting up to that output node is essentially has a desired output of either 1 or 0, depending on whether the pattern presented is in that particular class or not, right. So, this is like a proper generalization of the two class idea to k classes. So, in a test pattern, we can decide the class based on which of the output nodes have the maximum value, because we want the, if it is in class J, DSC is such that the jth component of DSC is 1. So, whenever it is in class J, jth output node should be closer to 1. Hence, when you give me a new test pattern after learning, I calculate all the k outputs, whichever output is closer to 1, means whichever output is largest from using sigmoidal accretion function, whichever output is closer to 1 is same, whichever output is the highest value, we will put the pattern in that class. As we shall see in the next couple of slides, since actually we are minimizing square error loss, as we have seen earlier when we did linear regression, we can think of each output node in the structure approximating the corresponding posterior probability. As you seen in linear least squares also, we are essentially trying to approximate a posterior probability. So, here when we use this kind of representation, the network is allowing us to get good approximation of posterior probability. See why? Essentially, what are we doing? To learn the weights, we are minimizing this. This is the output of the network, the jth component of the output of the network. This is the jth component of the desired output dj. We take square sum over j. This is what I am minimizing. So, for a particular vector, let us say in some class, all other components except this component will be 0. Okay. So, if we consider the jth output node, its desired output would be 1 whenever the input pattern is from class J, otherwise it is 0. So, this is the reason. So, essentially it is still trying to learn in what can be called a two class context, and this is the reason why minimizing the squared error would result in approximating the posterior probability function. More precisely, let us say given two random variables x and y, I am trying to find a function g to minimize the expected value of gx minus y whole square. My square error loss is simply an empirical risk of this risk. This is the true risk of the squared error. So, I can think of g as the network, x as the input. So, g of x is the output of the network when x is given as the input. So, g is the network function, y is the desired output. Okay. Now, here if we are considering only one node, so this square is what I am minimizing. Then we know that the best function g is expected value of y given x, right. This we have proved some time back. See, y is binary, the conditional expectation of y given x is same as probability y is equal to 1 given x, which is nothing but the posterior probability function. So, the best function here is the posterior probability function. So, whenever I am minimizing this expectation, the best g is the posterior probability function, because this is what I am minimizing in that network with the training inputs 1 or 0 for each one of the output nodes. Each output node is correspondingly approximating the each output node is approximating the corresponding posterior probability. Right. Hence, our representation in the multi-class case, that is when I put as many output nodes as there are classes, and then represent each class by a k dimensional vector where jth component is 1 and all this 0. That representation would make the network learn the posterior probability function. That is the reason. So, the first output node will learn the posterior probability function for the class 1, second output node will learn the posterior probability function for class 2 and so on. Right. And hence, that is the reason why if I take the max, it is essentially trying to approximate the base classifier. Okay. So, in that sense, this particular structure of having as many output nodes as their classes is quite good for multi-class case when we want to use a neural network of this kind. Okay. So, we are almost done. So, we can say neural network models are seen to be, we know how to train neural networks for learning functions, for learning classifiers. We can learn nonlinear regression functions, nonlinear classifiers. We are essentially doing empirical risk minimization and square error loss function, and for minimization we are using gradient descent. The back propagation is a very elegant way of doing this. So, the model, the algorithm, everything is clear, and while the course, so we can't see too many examples. Neural network models are seen to be quite good for classification regression. They have been used in many applications. Most of your MATLAB toolkits and so on always contain this now, and in many applications they seem to be quite effective. But to actually use them, now we are moving to realm where models are complicated. To actually use these models, there are many parameters of the network that need to be chosen. You have to choose the hidden layers, number of hidden nodes, step sizes in the learning algorithm, activation function types. There are a lot of things to be chosen, right? And the gradient descent can get stuck in local minima. So, we want to get to better local minima. So, can I tweak my initial points, or there some other things I can do for the gradient descent? All these are important. Of course, there is very little theory in this, but in the next few slides I will discuss a few practical tips of how to make learning with neural networks more effective. Okay. So, basically the issue is, so that is why I call this the art of backpropagation. The science is over now, but in practice it has to work well. So, you use a network for learning functions, but it decide on many parameters, right? Number of hidden layers and hidden nodes, activation function for nodes, whether we to use online or batch mode for learning, what the initial values of weights to use. The learning algorithm is an iterative gradient descent. So, we to start somewhere, and because the gradient descent converges to local minima close to the starting point, initial values can make a lot of difference, right? How do I choose step sizes, other issues learning algorithm. See, the first two are how to fix the network structure. Last three are what can I do about the learning algorithm, right? All these need to be discussed. We need some tips for all of them. So, we are going to look at each of them. Okay. Okay. First, about the structure. Before we can learn the weights, we have to fix the structure of the network, right? That we know. Backpropagation only learns the weights. After the structure of the network is fixed, because we need to do the forward and backward computations to do backpropagation. So, the structure of the network has to be completely fixed before I can do backpropagation. Now, we have seen a theorem that says one hidden layer is enough if you have sufficient hidden nodes, right. So, basically we can always choose one hidden layer, but we do not know how many hidden nodes to use. There is no theoretical thing about how many. So, we just do trial and error essentially. So, on the other hand, I do not want to use too many hidden nodes, because I may overfit. Okay. Well, I will come a little while later to what overfitting is. Sometimes using two hidden layers might be better. Suppose I have got a 50-dimensional feature vector. Let us say I want a 3-layer network with one hidden layer, and let us say 10 hidden nodes. Because input is 50, input layer is 50 nodes. I got 50 into 10, 500 weights, and then 10 into 1, let us say one output node, 500 plus 10 weights. But suppose I put these 10 hidden nodes not as in one layer, but one layer of 5 and the next layer of 5. I use two hidden layers. Then input layer to the first hidden layer is only 500 into 5 is 250. First hidden layer to second hidden layer is 5 into 5, 25, and another 5 for second hidden layer too. So, instead of having 510 weights, I am doing with 280 weights. Now, whether 10 hidden nodes in one layer is equivalent to 5 each in 2 hidden layers, nobody knows, but very often this is one reason why I may use more than one hidden layer, right. So that I can reduce the number of weights. So, in practice one never uses very many hidden layers. You try 1 or 2 hidden layers, not much more. Number of hidden nodes is always by trial and error. We do not want to put too many, you put just a few to see whether you are getting good enough results. If you are not getting good enough results, then you would like to increase the nodes. How do I decide how few is few? It turns out that the VC dimension of these models is of the same order as the number of weights plus number of nodes. So, we know that we need an order of magnitude more than VC dimension examples. So, depending on how many examples we have, we would like to constrain the network structure. Very often in these networks it is not possible to have examples which are 10 times the number of weights and so on, because the weights are very many in this, but we still do not want to be too large. At least we want the number of examples to be of the same order as the weights. We need at least a little more than the weights. So, that also determines how many hidden nodes we will use. we know how many training examples we can afford, and that determines how complicated the structure can be. So, this is about the only guide we have. We know the VC dimension is of the order of number of weights plus nodes, and hence looking at the number of training samples we have, we would like to keep our total number of weights down, and we use that as a guide to decide how many hidden nodes we can afford. Okay. So, that is about all I can say about hidden nodes. Most of the time it is trial and error, and a little later in the course we look at what do we mean by trial and error. We look at techniques called some of the techniques such as cross validation, which will help you to try out different number of hidden nodes and say which is better. Okay. Now, what about activation functions? Once again, the theorem that we stored says that it should be smooth monotonically increasing functions. Of course, monotonically increasing or not, we anyway need smoothness, because to do gradient descent we need differentiability of the activation function. So, that much is certainly true for using backpropagation. Given this, what can I use? The most commonly used activation functions are sigmoid and tan hyperbolic, hyperbolic tangent and sigmoid. Between them the choice depends on what kind of output you need. See, sigmoid gives you output range only 0 to 1, whereas tan hyperbolic gives -1 to 1. As you said, we can always scale the output. We can make the output node, so actual output to be k times sigmoid or k times the tan hyperbolic. So, but the question is whether I need output of only one sign or I need outputs of both signs, right. So, depending on the need, if I need outputs of both signs, then I have to use a tan hyperbolic kind of function, otherwise I use sigmoid. These two are the most often used functions. There are many other functions one can use. For example, e to the power of minus net input square, that is also a nice function, decreasing function. So, there are other kinds of activation function that can be used in practice, but most often, I mean, in a vast majority of applications, people use either sigmoid or tan hyperbolic activation functions. Okay. As I said, we have to always linearly scale the outputs to match the actual output range, right. Inputs okay, we will come to the input side later, but outputs, if the output range is beyond 0 to 1 or beyond -1 to 1, then we may have to linearly scale the outputs. Next, let us consider all the issues that deal with the learning algorithm. Okay. What are the issues of the learning algorithm? First, should I do online or batch? Just to recall, for each training example, I put that input at the input of the network, calculate the output. Once I have the output, I use the desired output for that input to calculate the error. For that error, I can calculate all the gradient, all the partial derivatives using backpropagation. Now, I have to do this for every one of the inputs. In the batch mode update, I keep the weights all fixed, apply inputs one by one at the input end of the network, calculate the outputs, errors, and through backpropagation all the partial derivatives, and then do one gradient descent step, one update of the weights. In the online mode, I put one example, calculate the output, immediately the error, backpropagate, find all the partial derivatives, and immediately update the weights, and then apply the next example. Of course, when I do this in the online mode, I can apply the examples in some order. So, going through all the examples once is called an epoch normally in the online model. Now, most often theoretically it may not make much difference. As I mentioned when we did the linear models and when we first looked at the online and batch things, the LMS algorithm, if the step size is sufficiently small, then both online and batch updates have the same asymptotic behavior. Now, in this particular case, when using backpropagation, we are doing gradient descent on a very high dimensional and very highly nonlinear objective function, and we are using a constant step size gradient descent. So, we have to anyway use a very small step size, because you anyway use a very small step size, both of them will have similar asymptotic behavior, and so both of them will converge to local minima. So, the choice is not so much about whether they are converge or not, it is about what may be more convenient to implement. If you have a large number of examples, online is more convenient. So, of course, batch mode is nice because batch mode is exactly same as the right gradient descent of the function. So, I can actually update batch mode, but if you have a large number of examples, online might be better, because otherwise we may have to run through some 1000 examples. So, to do 1000 function computations, and then only my weights will get updated by a small bit. I have to anyway use a small step size, I can't afford to use very large step size. So, even to change my weights by a small amount, I may have to do lot of computation, calculating outputs for 1000 input patterns. So, I might be wasting too much computation. So, this is the reason why if I have a large number of examples, very often online is done. Another is, I can, when I do online, unlike batch, I can possibly use some stochastic, some kind of randomization techniques to try to get to better local minima. This is a gradient descent, so you need all kinds of tricks to get good minima. So, for example, from epoch to epoch, I do not have to present all my examples in the same order. So, maybe in one epoch of the online algorithm, I present examples 1 to n, and in the next epoch I go from n to 1, or I do a random shuffling of the examples for each epoch. Very often that kind of things help in finding good minima. Okay. So, it kind of gives an extra shake to the algorithm. So, these tricks generally find you good minima. Okay. Another thing that is often needed is to normalize the inputs or the feature vectors. Why? If different components of the input vector x have different very widely differing range of values. So, if one component goes from 0.1 to 0.2, another component goes from 1 to 10,000, then ultimately you take these inputs, multiply by weight and add them, right. I get into all kinds of numerical problems, right. Even my weights have to traverse very large dynamical range, and that might be very difficult for the gradient descent algorithm to find. So, because of that, I would like to have all the components input to roughly have the same dynamic range. One way of doing it is to linearly transform every range into -1 to 1. So, simply find the max and min for each of the input dimensions, and then simply linearly transform that input, so that all components will be -1 to 1. But what often gives better performance than this is to transform these features, so that each feature, that is each component of x, can be thought of as a 0 mean unit variance random variable, right. So, that I am not really making it strictly between -1 to 1, but I am transforming them so that each of them would be a 0 mean unit variance random variable. How do you do that? Let us say this is the feature vector with m components. Now, I have training samples xs, that means I have a sample for each one of these components, n such training samples. These can be taken to be IID. So, if I think of x1 as the random variable corresponding with the first feature, x1 yes as equal to 1 to n or IID samples of that random variable. So, I can find the mean and variance. So, the mean, mu j and variance sigma square j of the jth feature, as these are the maximum likelihood estimates. In general, both of them are sample mean and sample variance. These are very good estimates for most kind of models. So, I can estimate my mean and variance of the of each of the feature components. Once I do that, I can transform the original example xs to a new example xs tilde, so that each component is now become tilde. So, the tilde component xs x tilde j has become xj minus mu j by sigma j. Sigma j is of course square root of sigma square j. So, as you know, because xj has mean mu and variance sigma, xj tilde will have mean 0 and variance 1. Right. So, this transformation will kind of make all the feature vectors to be 0 mean unit variance random variables. Okay. And often this kind of transformation works better than simply doing a linear transform to bring all feature components to -1 1, because here by this 1 by sigma j I am kind of also normalizing the variation in each of these random variables. A matter of fact, here of course I am only individually making them zero mean unit variance. I am not worrying, I am not doing anything about correlations between them. A similar linear transformation is possible to do, so that different feature components can be uncorrelated or decorrelated, so that learning can be much more effective. Okay, if you have independent features, we'll look at such transforms when we do what is called PCA, principal component analysis. So this is about normalizing inputs, right? So I have to normalize inputs. Another factor that affects performance of any gradient descent is where you start, right? Generally it converges to local minima closest to where you start. So where you start becomes often very crucial, and because the very high dimensional space, a simple minded starting point like take all weights to be 0 is never a good starting point. See, you remember that I also told you there is a lot of weight space symmetries. If I permute the nodes in the hidden layer, right. So I get a different weight vector, but which effectively represent the same function, which means the minimizing weight vector will not be unique. There will be many weight vectors where minimum can be achieved, and given so many such weight space symmetries and degeneracy, all 0 kind of initial point is generally not a good initial point. So there is not much to say except that often small random values for initialization are better. Okay. Instead of all being same, some initial random variation will allow the gradient descent search to be much more effective. Normally what one does is to choose the initial weights from some distribution, choose them randomly, where the distribution has 0 mean and variance 1 by nu. Okay. Where nu is the in degree. So depending on how many weights are there for each node, or for all the weights of one node, I use one distribution. This 1 by nu variance is once again just a guidance. For example, I can decide on the range of weights. I can think them to be uniform from minus a to a, where a depends on the in degree. Right. But basically the idea is that for nodes that have large number of weights, I do not want too much variation. So, essentially backpropagation is a gradient descent in a very high dimensional space. So, a gradient descent kind of optimization in a high dimensional space has a lot of problems. So, backpropagation will have all the problems associated with any such gradient descent algorithm, right. For example, it gets stuck in local minima. So, very often what people do is you use multiple starting points. So, run it from many different starting points and try to take the best one you get, right. This is also done, and we know it gets stuck in local minima, it is very slow, gradient descent is very slow and so on. There are a couple of things that we can do to improve the algorithm, right, improve the gradient descent itself. Here are a few such things. This is called backpropagation with a momentum term. What you do is, if I write delta Wij Lt as Wij Lt plus 1 minus Wij Lt, essentially what is the algorithm we had earlier? Wij Lt plus 1 equal to Wij Lt minus the gradient, right, minus lambda times the gradient. So, if I take this difference to be delta Wij T, so my earlier algorithm is delta Wij Lt is simply minus the gradient. This is equal to minus lambda dou j by dou Wij Lt. This T simply means that this gradient is evaluated using the values of weights at T. So, what I am doing in this algorithm is, in addition to the usual gradient step, I am adding one more step. What did the second step give me? This is delta Wij Lt minus 1, that is Wij Lt minus Wij Lt minus 1. So, essentially in addition to the current gradient, I am adding a term which is proportional to the direction in which we moved in the previous iteration. If you think of it as vector this is the component equation. If you look at the vector equation, then in addition to the gradient vector, this one adds a component which is the direction in which I traverse in the previous 2 iterations. So, I am currently t to t plus 1 iteration. This is the direction which I travelled between t minus 1 to t iteration. Right. So, at each iteration we had a small term which is proportional to the direction in which we moved in the previous iteration in addition to the gradient. What does that do? This essentially is what a conjugate gradient descent algorithm is. Of course, the proper conjugate gradient needs to correctly find that previous direction. It has to be the weight for that is to be determined based on the proper conjugate directions. But essentially you can think of this as the Poorman's conjugate directions method. So, this essentially adds a kind of conjugate directions kind of flavor to the gradient descent and hence speeds it up. So, now we have 2 step sizes, a lambda the step size for the gradient term and the gamma is the step size for this term is often called the momentum term. Okay. So, if both the step sizes of the gradient and the momentum are sufficiently small, then this algorithm can also be shown to converge to local minimum. So, essentially it does not change the asymptotic properties, whether that term is there or not, I still go to the local minimum, but in practice this term considerably speeds up the algorithm. This is just like gradient descent and conjugate directions, where conjugate directions method is faster even though it also converges to the same minimum. Okay. So, in practice one always uses back propagation with a momentum term, nobody ever uses it without the momentum term. Another simple strategy one often uses for learning is what is called weight decay. What do you mean by weight decay? We say from time to time we replace each weight with 1 minus epsilon times itself, where epsilon is some positive number. So, I just shed a part of the weight. The idea is that this way weights do not blow up, I do not let weights become very large. Okay. We can do it in every iteration, we can do it after fixed number of iterations and so on. Why does this work? This is essentially implementing gradient descent on a regularized disk. We seen regularized least squares last time. So, what is that? We are essentially trying to minimize j, the sum of squared errors. Suppose instead of j, we want to minimize j tilde, where j tilde is j plus half epsilon times norm w square. So, this is exactly like the regularized least squares that we discussed earlier. Instead of just using the data error, we also use a model complexity term, and for squared error we seen that the good complexity term is the square of the weights, the norm of the weights. So, what does that mean? Now, if I do gradient descent on j tilde, now this will be the usual gradient minus lambda j this, and this will give me minus epsilon, the 0.5 I put here so that this 2 will cancel. This is nothing but the square of each of the components. So, if I take a partial derivative of any one component, I get that component there. So, making each wij 1 minus epsilon times the wij from time to time is simply that on top of the gradient descent, I am just implementing the regularized least squares. So, essentially weight decay is same as doing a regularized least squares gradient, that doing gradient descent on not just the sum of squares of errors, but sum of squares of errors plus a regularization term, where epsilon now plays the role of the regularization constant. Okay. So, these are all the various tricks that one can use to make the gradient descent work better. So, to sum up, to learn weights in a feed-forward network, we are minimizing empirical risk under squared error loss, and gradient descent and hence back propagation is only one method to do such optimization, right. Let us not forget that what we want to do is minimize empirical risk under squared error loss, and to minimize we decide to use iterative gradient descent, and to calculate gradient we are using back propagation. There can be other methods for the same objective function. I can use many other methods for minimization. For example, I can use Newton's method, I can do any of the quasi-Newton methods such as Powell's method or BFGS and so on. Right. There are many Newton or quasi-Newton methods. All of them need second order partial derivatives. Sometimes they need to invert the Hessian, sometimes Cauchy-Newton methods do not want you to invert the Hessian, but all of them need the second order partial derivatives. As it turns out, if a back propagation like method exists for first order derivatives, a similar procedure should exist for second order derivatives, even though it is a little more complicated. It is possible to get the second order partial derivatives also using a back propagation like method. So, I can use such Cauchy-Newton methods. That is not all. So, we can use many operation techniques to learn the appropriate weights. Of course, squared error loss itself is an arbitrary choice. I can use other loss functions, right. So, there are many variations are possible within these networks. I have many other variations to learn within these networks. While all such variations exist and people have used other optimization techniques, also rarely some other loss function. The most often used algorithm is back propagation with these models. Okay. Now, this completes the multilayered feed-forward network models with sigmoid activation functions, where each node takes a linear sum and passes sigmoid. But these are not the only kind of neural network models one can have. There can be other network models. Okay. While these are the most popular neural network models for classification and regression, one can have other such network models. Let us just quickly look at what do I mean by that. Let us go back to the old three-layer network. Essentially, the three-layer network function depends on, it is a linear sum of the outputs here. So, given the inputs, I first calculate these outputs through any other function and then take a linear sum, right. So, the function represented by this network can be written as y is equal to sum over j, the hidden nodes, beta j into sum this. This is the actual sigmoidal activation function and each node does linear sum. I can rewrite this function as this f of all this can be written as some phi of x, the input vector, comma theta j, where theta j subsumes all wij's, bj's, everything. So, this is some function phi, which is a function of x and some parameters, and the parameters are specific to each of the hidden nodes, each of the j's, right. So, there can be functions phi that result in continuous function approximation. There can be ways of representing any continuous function like this also, because this is just like this is also beta j phi x, phi j x, but where I have tunable parameters here. So, it is not a fixed basis of expansion. This, okay. So, this is also a representation where the basis functions are learnt, if you are learning theta j from and I can think of this as another kind of a three-layer network model, where I can still think of this as a three-layer network, where phi x comma theta j is the output of the jth node and then multiply with beta j and sum it up, right. So, I can have a different three-layer network model whose output is like this, and this is also is not a fixed basis function, but basis functions adopted. So, these are the kind of networks, these are called perfect interpolation networks, radial basis function networks and so on. These are the network models that we will consider next in the next class. Thank you.